So I teach a lot of classes where I can't talk about anything about my research because I used to be a pure mathematician. That means a mathematician that just works on math because they love math. But now I do a lot of applied math. I run a Center for Obesity Research on campus, and we have a weight management clinic, and we work with the top researchers and medical doctors around the world on problems related to obesity. So one of the things that we always want to look at is how do you measure someone's fatness, we call it adiposity, by just a few easy calculations. Because if you come to our clinic, we can't take you and do an MRI. First of all, we don't have an MRI. We do have an ultrasound. We don't have an MRI. So we need some quick way to tell, well, whether you are eligible to even come to the clinic. So the easiest way to do this is something called body mass index, or BMI. BMI is a measure of your weight in kilograms divided by your height squared. Where did this come from? Believe it or not, it was a mathematician that came up with the concept of BMI. This is a picture of Quetelet. He's a French mathematician who years ago, not for the reasons of actually measuring adiposity in humans, but for another reason, he wanted to look at the population and figure out their body shapes. And he came up with this notion, he experimentally came up with the fact that if you take weight and divide it by height squared, it gives you a good metric of that person's body shape. What's his name? Quetelet, and he's spelled Q-U, it's spelled differently than it sounds. Q-U-E. Yeah, it has an L-E-T at the end. Yeah, you can see a signature there. So people criticize BMI all the time because you could be someone who's really in shape and have a high body mass index. So a body mass index that ranks you above 30, you're classified as obese. And there's many bodybuilders who are in perfectly fit shape that have hardly any body fat on them that are classified as obese. And we also get that with elite athletes. You get a BMI doesn't really give you a good measure of their adiposity. So it's under attack all the time. But to me, as a mathematician, I think it does pretty well for just two measurements. I just get your body weight on the scale, I get your height on the statometer, and with those two measurements, I can tell you approximately where you stand in terms of fatness. And not very few of us are elite athletes. So to me, most of the population does fall under this BMI. However, one of the things that is criticized for is doesn't pick up location of fat distribution. And I don't know if you've heard of bad fat, the belly fat, the stuff that I seem to always accrue over the break. This is a great thing about Montclair. Once I'm on Montclair, I never eat anything. I just try to get home. The food is better here than it has been in the past, but still. Is there a way, they call that visceral fat, by the way, and we have an ultrasound in our clinic where we train the students on how to use the ultrasound to pick up that visceral fat at the waist. How do you somehow tell with an easy measurement, though? Not everybody has an ultrasound. Do you have an ultrasound at home? Right. Do you have an ultrasound at home? So not everybody has an ultrasound at home. How many of you have an ultrasound at home? Come on, Adele. Fast up. So that's the problem. We don't have MRIs and ultrasounds at home to pick up our visceral fat. What we do know is BMI is already correlated with whole body fat, but what about the bad fat that's at your belly? It also correlates really good to waist circumference. Waist circumference is when you take a tape measure around your belly, and it tells you how wide you are at your belly. And waist circumference correlates okay to belly fat, which it probably should, right? You're looking at an outside measurement and trying to tell what's on the inside. BMI, though, is related to this waist circumference. That doesn't make sense, but it does because of geometry. And here we are right on your conic sections. Here for conic sections has nothing to do with planets at all. It has to do with medicine. So if you think of the human body as being in a tin can, a cylinder, then it turns out that your height would make the height of that cylinder, and your circumference would be your waist circumference. That makes absolute sense, right? We have a geometry. Our bodies are geometrical in some ways. So you don't have to worry about the equations here. I actually presented this at a medical conference, and I'm sure nobody worried about the equations. But I can actually tell you why geometrically, body mass index is related to your circumference. They're connected to each other. It comes from the formula for the volume of the cylinder. Volume of the cylinder connects the two. So they're related to each other. And that's the relation at the end. You can actually go through some calculations and show that the two are related to each other. But the problem is BMI is a two-dimensional line. That's why it doesn't give you distribution, right? It just slices you down as a tin can like this, and that's all it does. So the problem is, can we do better if I had a third measurement? Can we improve the geometrical modeling? And we are constrained by what we can do. Like if I take you into clinic, I'm not going to have, we actually see patients in our clinic here. I can tell you they don't want to spend their whole lunch hour getting wrist circumference and neck circumference. They just want a quick in and out, get me in and out of there. So we're constrained by things that are easy. And that would be waist circumference, hip circumference, and your body weight and your height. You don't want to go beyond that, or else you stress your patient out. I mean, when you go to the doctor, you won't want to spend 2 hours there. People have liked to look at this experimentally. Like, what if I take these measurements and then combine them in this way? Will they tell me, are they related to their abdominal fat in any way? But what we said is, why can't we use ellipses? Here we are. Do you ever think of an ellipse ever being used in medicine? It is. This is actually used across the country right now, this thing that I'm showing you. And what we did is we said, okay, the human body, I don't know about you, but I don't feel like a tin can most days. Usually I look in the mirror and go, oh, that's my hips. I look more like an egg, unfortunately. And I think most people look like an egg. Probably men would look like a cylinder more than a woman. But I certainly don't think most of us in here look like cylinders. We look more like this. We have an oval shape if you encapsulate our body. So if I took an oval and put your body in an oval instead of that tin can picture you saw in the beginning, well, it's going to be one of those ellipses that stand up, not the one that lies down unless you're bent. Right, so it's a standing up ellipse. This part here I can get from waist circumference. This part here I can get from your height. So 2 measurements to get that picture. Your height makes what we call the long axis, and your waist makes the short axis. So remember I told you that thing about planets? That there was a way that you can figure out if an orbit is close to being a circle orbit. That's a number called eccentricity. You can actually calculate it. I'm not going to show you in this class how to calculate it, but most pre-calc classes you make students do that. So it's a number that you get directly from the formula of the ellipse that tells you how close that ellipse is to being a circle. And for this Earth, it's pretty close to being a circle. So the closer that number is to being 0, the closer you're to being a circle. Closer, I probably have this backwards. Closer that number is to being a 1, the more you're standing up like a straight line. Right? Yeah, I got it right. 1 is a straight line. So if I was really, really lean, I would be almost like a straight line. I wouldn't be like a round circle. Right? So it would tell me my body shape. That number would tell me how close I'm to being a circle. So the further I am away from being a circle, the more lean I am. The more I'm like a circle, the more I look like Santa Claus. Okay? Now I have a way to take that ellipse and use one number to tell me how round that person is. And it's different than body weight, right? That would take care of the problem with athletes, because you wouldn't have you wouldn't have that problem with, you now have body distribution. So here's a picture. 3 people, same BMI. This one's really tall and lean. This one is muscular, and this one's a little pudgy. But they all have the same BMI because I can't tell, I can only get height from that. I can compare the 3 by their circle, by their ellipses. The tall person would be this one right here, because they're not as round. So they'd be more like a standing up stick, right? And the pudgy person would be this one, the outer one. So now I can map them to their eccentricity and see how round they are by looking at them in terms of an ellipse. So I'm going to skip this. We made a calculator. Here's the thing, I work with a lot of doctors. They don't want to see the formulas. Sometimes I don't think they even want to know me because, I start talking about this and that, and they're like, their eyes just kind of glaze over. They don't want to hear it. They want to know, can I build a model and will it be useful? And so we have a programmer on our team that takes the models that we develop so that they can be clinically used. So here's the software that we've made. You input your own personal things up at the top. Your race, your age, your gender, your height, your weight, your waist circumference, and hip circumference if you have it. And what you'll get is a picture like this below. This black picture is your roundness, your body shape. The green area right here is a healthy body shape. So if you're far away from the healthy body shape, you know what goal you have to reach to change your body shape to get to. If you're inside, we actually had a student that was inside the body shape, inside here. Remember, no cell phones. Keep the cell phones off the desk. So if you're inside here, your body shape is probably too lean. And we actually had a girl in our research team who'd always say, we're gonna run an overfeeding study and move you back out to the green area. I want to show you how this works. So this is a woman who was in a walking intervention. All they did is put a pedometer on her and said, walk. And this is what happened to her in 4 months. This was her circle, or her ellipse, when she began the intervention. And this was the healthy region where she was supposed to strive for. And in 4 months, she got much closer to that healthy region by just walking. So this is not a calorie cutting intervention. It was get some activity in there. It would account for it. Even if she didn't lose weight, she's changing her body shape and reaching a healthy region. So we try to use this on people where body weight is not the only measure of your health. It could also be that your shape is not the right shape. And by the way, this calculator is freely available, and if you want a link to it, I'll send you the link so you can. The provost wants you to know that he's in the green region. The provost of your region and your dean of your college is also in the green region. You should know that. That's the first thing they did, they tested it out. We're building something like this for children for a hospital in University of Florida right now because they want to show the children something. Like you can say, okay, this is where you need to be visually so they can see it. So this is we're really using this to actually change people.